Okay, welcome back. This is ECON356. Today we are going to continue where we stopped. Last time I did not want to overload you with information, so today we are going to talk about the first steps in inferential statistics. Okay. Like we said, inferential statistics is simply using information from a sample to make judgments about the population. So I'm going to share my screen just to illustrate the point. Okay. All right. So I'm going to start here. Okay. So what's inferential statistics? That's today's lecture is going to be about inferential statistics. Like we said, it's using information from a sample to make a judgment about the population. Because sometimes getting information on population can be difficult because you cannot truly always measure a population. Sometimes getting the information from the population can be costly. And so time could be also a factor. It could be time consuming. And by the time you get all the information from the population, then the information that you're looking for will be overtaken by events. And so you want to be able to make a timely decision because you need the information right away. Now, there are two things we're going to do in inferential statistics for this class. And again, we're just making it easy. One is to do confidence intervals, and the other is to do hypothesis testing. As a matter of fact, the information you get from confidence intervals could actually be used for hypothesis testing. And sometimes hypothesis testing just is based on a confidence interval estimation. Okay, so what is a confidence interval? Okay, what's a confidence interval? And for this class, we are going to focus on confidence interval for the mean, but you can do confidence interval for the variance, and so, but we're going to focus on confidence intervals for the mean. Okay, so when we are trying to do a confidence interval, what is our problem and what is our method? Okay, now, what is the problem in doing a confidence interval? Okay, and what we do is a confidence interval estimation. Okay, all right. So let us say we ask ourselves a simple question: what is the problem? The problem is that we are trying to estimate, say, an average, and I'll give you an example. Let us say we during a rainy day or just for any reason at all, we want to ask ourselves, what is the average travel time that a student takes to travel to school from wherever they are? What if we wanted to know what is the average amount of money that a customer spends at a restaurant? You own a restaurant. You want to give yourself an idea, what is the average amount of money that customers that come to your restaurants spend? So the problem is that we don't have an idea of the population average. We don't know what the population average is, like the average amount of money that the customer spends at lunch or in your restaurant. Okay, the average time that it takes for a student to get to school from wherever they start. So we don't know the average. What we're actually trying to do is we are trying to get an idea of the true population average, and we'll call it the true population mean, okay? And the true population is mu, okay? So that is the problem that we want to solve. What is the true population mean? All right? All right. So our objective is that we want to estimate the population mean using the sample mean. The population mean is mu. The sample mean is x bar. Okay? Now, in order to do this, we have to assume a probability distribution. And so the question is, what probability distribution do we use? The probability distribution we use is the probability distribution we believe that the data that we have follows. So the data can follow any kind of probability distribution, and we have to use that probability distribution to do our confidence interval estimate. So for our purposes, we are going to use the normal distribution. So I'm going to go back here, okay? We begin from what we call the point estimate. The X bar that you see there is the sample mean. So we get information from the sample, and we want to use that information to estimate the true value for the population, okay? So you ask, what is the average amount of money that a student spends at lunch at the canteen at McGivers College? So we take the first 100 students that come to lunch. It could be in one day, it could be over 2 days, it could be over 3 days. But we just randomly identify 100 students and record how much they spend for lunch. Now that's a sample, because it's not every student that ever bought lunch at Medgar that we're going to be looking at, because we're going to have difficulty identifying every student that ever bought lunch at McGivers College. So we take a sample of 100 students, we take a sample of 50 students, we take a sample of 30 students, any sample size. And when we calculate the average amount of money that that sample spends, we'll call it X bar. We'll call it X bar, okay? And our objective is to use X bar to estimate what the true population is, okay? Which is what is the true population average. If you were to get the information from every single student that ever bought lunch at McGivers College, what would be the true population mean? Mu, okay? We don't have that information, we couldn't get it, and so we use a sample to estimate mu, okay? We use a sample variance to estimate the population variance. We use a sample proportion, P, to estimate the true population proportion pi. For example, what percentage of students will buy a hamburger instead of, will buy a chicken burger instead of a beef burger? What percentage of students come to school by public transportation compared to coming by private transportation? This is an example of proportion estimate. So like I said, in this class, we're going to focus on the mean. We're also going to do some proportion, but we will not estimate variance, which is S squared. S squared is the variance. We're not going to estimate variance. We're not going to estimate standard deviation. We're going to calculate standard deviation and variance for our purposes. But to ask ourselves, what is the true population variance, we will not do that. We will ask what is the true population mean, and we'll ask what is the true population proportion. All right. So now we're going to assume the normal distribution. We're going to do our estimation using the normal distribution. And so the first thing that we're going to do is to try to understand what is normal probability distribution. I believe that you covered this in your introductory statistics class. So we're going to ask ourselves, how do you use the normal probability distribution to implement inferential statistics? So we're going to step back a little bit and understand the normal distribution. Just a review, because I believe you already understand the normal distribution. This is going to be a review, but if you have questions at the end, you could also ask me questions. Okay. Now, in inferential statistics, as we said earlier, our subject is the population. Okay. We want to find out the characteristics of the population. It could be average income, average travel time, average GPA, average amount spent on money, average weight of fish in a fish pond. Okay. We use information from a sample N to make a judgment about the population. Okay. And the population is N, like big N. Okay. All right. Now, before we left the last time, we said that the normal distribution has a particular characteristic. Okay. The normal distribution is represented by some random variable. Okay, that is bell-shaped. The random variable is a hypothetical random variable, and I'm going to call that hypothetical random variable Z. Okay. The probability distribution of the random variable Z is symmetrical about the mean mu. Okay. It is asymptotic in the sense that when I show it to you, asymptotic means that this tail goes on forever on the right side, this tail goes on forever on the left side. So it never touches zero. That never touches the line. So we say it's asymptotic. Okay, that's what that means. Okay. Now, as we said the last time, we can see the normal distribution is bell-shaped. It is symmetrical. And so the value of the mean is exactly in the middle. And I'm going to put some information here. Okay. Normal random variable Z. Okay. Now, the mean of Z is 0. Okay. The mean to 0. I'm going to make sure that I get that. That should be what it is. The population mean is 0. And the population standard. So the random variable Z has a mean equal to 0. Okay. And a standard deviation, just say here, mean mu. Okay. And the standard deviation sigma is equal to 1. Okay. That is a characteristic that you need to know. All right, so you need to know that. And when you go back to this distribution, the value, the mean 0, comes squarely in the middle. And so the area of this normal distribution curve is equal to 1. It's always equal to 1. So that if the mean falls exactly in the middle, 0, that means the area of the curve on this side is equal to 0.5. And the area of the curve on this side is equal to 0.5. So 0.5 plus 0.5 is equal to 1. Okay? And so let's look at some of the uses of the normal distribution. Okay? And the way we make use of this characteristic of the normal distribution. What do we do with it? That helps us. And so we ask ourselves, suppose we take a value, say at some point here, say z is equal to 0, the standard deviation equal to 1. Okay? And we ask ourselves some simple questions. Okay? If you, and I'm going to, okay? So we'll calculate areas on the z. We ask ourselves, what is the probability that z has a value between 0 and 1. Matter of fact, okay. So essentially this is to ask the question, what percentage of the area is between 0 and 1? Okay. The other question, you ask yourself, what percentage of the area is between -1 and 0. So you ask yourself another question, what percentage of the area between -1 and 1? Okay, and so we're going to ask a number of questions. What percentage of the area of the curve is between -1.7 and 1.5? Okay. What percentage of the area of Z is greater than 1.92? Percentage of the area, or probability Z less than 1.67. And I'm using arbitrary numbers here. Okay, so we're going to go through each of these. Okay. Now again, this is a review. Okay, remember this is a review. So it's an, I'm assuming here that this is something that you already have understood from your first course in statistics. All right, and I'm not going to do those kinds of examples yet. So let's try to solve through some of these examples. Okay, I'm trying to.
Dr. Egby?
Yes.
I have a quick question.
Sure.
Will you, during the office hours, like, can you go over like the assignment that's due this week on machines?
Yes, we will go over it, and if we're not able to get there, we will move the assignment. I'll keep moving the assignment until we get there. But I need for you to understand, because the assignment of machines depends on what we're just talking about now.
Okay.
If you feel confident that you can do it, then we'll just go and do the example, and that will be that. I'll be very glad to do that. Okay.
Okay. Yeah,
Now,
thank you.
Now, in order to be able to solve these problems, the equation of the number distribution has already been solved. Okay, so you don't need to solve it, and I'm not going to represent the equation here. But our ability to resolve the assignment is going to be based on our understanding of number distribution. So we're going to use the probability distribution table for Z. Okay, like we say, Z has a mean 0 and a standard deviation 1. So what we're going to do then is ask ourselves, under the area Z, what is the probability that Z has a value between 1 and 0? Now, you see the values of Z. Are you following me?
Yeah.
Hello?
Yeah.
You are? Okay. You see the values of Z. So Z has a value 0. So the probability that Z has an area between, what is the percentage of the area of Z that is between 0 and 1? So you come out the table here, this is 0 and 1. So the probability that Z, or the percentage of the area of Z between 0 and 1 is 0.3413. And so you read out the table, 0.3413. All right? Now, like I said, because Z is symmetrical, one step to the right is equal to one step to the left. Okay? And so you ask yourself the question, what is the area of Z between -1 and 0? The same thing. Okay? You go from 0 to 1. So you look at the absolute value, it's also equal to 0.3413. Okay? And so between -1 and 1, okay, between -1 and 1, since -1 is on the left side and 1 is on the right side, you add the 2, okay? You add the 2, and so you are going to get equals 0.3413 plus 0.3413, which is 0.6826. That is the area between -1 and 1, okay? Now, if you want to get the area between -1.7 and +1.5, you realize that -1.7 is on the left and +1.5 is on the right. So you find the area here equals to area to 1.7 plus area to 0.5 and then add. Okay. So we'll go to 1.5, which is 0.4332, 1.7, which is 0.4554. Okay, which is 0.4332 plus 0.4554, and that gives you 0.8886. 0.8886. All right. So now we have to find the area that is greater than 1.93. Okay. So you're looking at the curve and you have 1.93 on the right side, and you're looking at the area above 1.93, which is, if you take 1.93 at this point and then the area under this small part of the curve, and so what you realize is that 1/2 of the curve is 0.5. So if you take the area from 1.93 and up, that means you are taking the 0.5 on this side and subtracting the area from 0 to 1.93, and what is left is on the tail end of 1.93. So we have 1.9, and we go under the curve here to 3, so we have 0.4732. So that will be equals 0.5 minus 0.4732, which gives us what? 5 minus 0.4732, which is 0.0268, 0.0268. So, which again is 2.68 cent. Now, we're going to apply this concept to simple estimation problem. Okay. All right. So now we've already covered that. That's the table we used. Okay. These are the things we already covered. All right. So now we're going to apply this to confidence interval estimate. Okay. Now, the confidence interval. Now, think about the concept of an interval. Like we said, we don't know what the true average is. We don't know what the true average is. But we want to use the information from the sample to estimate the true population average. Okay, and so in order to do that, we ask ourselves a simple question. When we are doing an estimate, a confidence interval estimate, we're going to be looking at two values. We're going to take a sample, and then we calculate the sample mean. Okay, so I'm going to go through a process here. Dense sample. Okay. Take a sample, calculate X bar, okay. Sample mean, okay. And then calculate margin of error, okay. And so, and subtract the margin of error. All right. Sample mean, which is going to give you a range, okay? A range means there's an upper value and a lower value. So you're going to say to yourself, I don't know what the true population mean is, but based on my confidence interval, it's going to be between 10 and 20. It's going to be between 12 and 18. It's going to be between 9 and 14, something like that. So you're going to get an upper value and a lower value, okay? So essentially, this is what a confidence interval does for you, all right? All right, so we're going to look at an example of a confidence interval. So now, like I said, the specified probability is called the level of confidence. So for example, you say there's a 95% confidence. There is a 98% confidence, okay? So you take the sample mean, X bar, and then plus or minus the margin of error, okay? And so I'm going to and the margin of error is what you have here. Remember about the Z we talked about, okay? The margin of error is that. See. Okay. So this is your margin of error. Z times sigma over root n. That is Z value times the standard deviation divided by the square root of the sample size. Okay. And that gives you the upper range. So let's see if we can illustrate this point here. Okay, I'm going to, so we're going to have the range of values X bar plus that. Okay. So then we're going to have X bar. I'm going to come down to what truly it is. What are we trying to say here? Okay. What are we saying? What does this mean? What we're saying is we don't know the true value of the mean. Remember, we are looking for the population mean. We don't know what the true population mean is. And so we say to ourselves, we don't know what the true population mean is, but when we calculate the true population mean based on our confidence interval, the true population mean will have a value between the sample mean minus the error and the sample mean plus the error. That is what we are saying. And so we're going to do an example that enables us to solve the problem in the homework assignment. So the question is, how do we get Z? How do we get Z? Z comes from the normal distribution table. How many standard deviations away are we looking at? Okay, Z comes from the normal distribution table. Okay, so here is an example. Okay, we took a survey of managers and a random sample of 68 managers reveals a sample mean of $49,000. The sample standard deviation is 8,850. Okay, what is the best point estimate of the population mean? Okay, our best estimate of the unknown population mean is the corresponding sample statistics. Okay, all right. Now, I'm going to change this. Okay, the sample mean, with a sample mean of 49,120. I don't know where this came from. 49,120, and the sample standard deviation is 1,850. All right. Okay. So we are asking to construct a 98% confidence interval for the income of managers in this industry. Okay. Now, this 98% confidence will come from your normal distribution table. And after we do this example, we'll go and do the homework assignment so that you can see what we mean. Okay. So a 98% confidence. Now, we are looking at 98% of the distribution of Z. Okay. Here is the Z table. So we are looking at a calculation that will put 98% confidence in our calculation. So, like we said, if we are looking at 98% confidence, I want one of you to tell me what is half of 98? Yeah, can somebody tell me what is half
46.
of 98? Nope.
No.
Take your calculator and divide 98 by 2.
40. 49, sorry.
49.
Yeah.
Is that correct? Good. That means that 49% of our calculation will be on the right, and 49% of our calculation will be on the left. You get the point now?
Yes.
Very good. So we go to the normal distribution table, and we look at 49%. So let's look for 49%. 49% is right here. 4.4901 is the closest we can get. Do you see 0.4901?
Yes.
Everybody see 0.4901?
Yeah.
Oh, good.
Yes.
Okay. So what value of Z gives us 0.4901? It's 2.3. We go down. 2.3 what?
0.03.
2.33. If you add 0.03 to 2.3, what do you get?
Or 2.33.
2.33. So the Z value we are going to use to get a 98% confidence interval, given that 49% is going to be on one side and 49% is going to be on the other side. So the Z value we're going to use is going to be 2.33. You get the point?
Yes.
All right. Okay. So we're going to use a Z value of 2.33. Okay. Okay. So for 98% confidence interval, Z is equal to 2.33. All right. And you can do that for every confidence interval. Divide the confidence interval by 2 and then go under the table and look for the Z value that corresponds to half of that. Now, what do we have? Okay. We have a sample mean. We use 4520 and a standard deviation of 3,500. The confidence interval is 2.33. So we take the sample mean for the 5,420 minus, and I'm going to make this a little clearer. All right. So I'm going to go back and change this problem here. 4520 3,500. I'm going to have to change this. The calculations again. All right. So everything is consistent with the solution we're going to do. So now we take the sample mean 45,420 minus the Z value we used times 3,500 over the square root of 68. We do it on the left side, we do it on the right side, and when we are done, what do we have? We have a 98% confidence that even though we do not know the true population mean, we are 98% confident that it is between 44,558 and 46,281. Okay? Go and check my calculations. If they are wrong, recalculate them, or we can do them right here. I don't know what happened here. We're using figures that come from the blues. Okay? All right. So This is our calculation. All right. So now we're going to do the homework problem. All right. We're going to do the homework problem. You can use SPSS to do this. But since the COVID came, we have not been able to truly do everything that we meant to do for this class. And I'm going to change this. Today is September 13. So we're going to save this file, and you're going to see it uploaded again for you. So I'm going to stop share this. All right. So somebody said do the homework problem. Am I correct?
Yes.
Okay, let's see if I have that homework problem up. All right. I'm going to share screen so that we know we are on the same page. This is the problem you're talking about, am I correct?
No, that's the one for last week. I'm talking about the machine one.
Oh.
Yeah.
Okay, did you do the one for last week?
Yeah, I did. I did on my own.
Okay, so you did the confidence interval.
Yeah, I did.
All right. So the one that you are talking about is the hypothesis testing. Am I correct?
Yes.
Okay. So let's see. All right. So I did not talk about hypothesis testing. So I'm going to move things a little bit off. I can see what you're asking for. But there's also a video on that if you look at week 3. Okay. Okay. All right. Okay. So it's the machine problem. Am I correct?
Yes, that's correct.
Okay, let me put it this way. You were supposed to test 3 different hypotheses there. And what I'm going to do, because I want everybody to do it right, okay? So next week, I'm going to give a big lecture on hypothesis testing then, and we're going to solve that problem. All right?
So you're postpone this assignment?
Of course, I will postpone it.
But will it be like, will it show up on Blackboard too? Like that you postponed it?
What do you mean show up on Blackboard?
Like, will the due date change on
Oh,
Blackboard
yes,
as
it
well?
will. Of course it will. I'm going to go change it right now while you are talking about it. As a matter of fact, September 18. Okay, I'm going to move it to 25. All right, so I've moved it. All right.
Okay, thank you.
The reason I'm doing it is that I need for you to really do it right. I need for everybody to do it right. All right. Okay. But also, before you come to the lecture, there is an office hour there. You see, let me share my screen so that you know what I'm talking about. Okay, are you seeing that on the screen? Office hour, ECON356?
Yeah, I see it.
Good. Go through it, and that will help you understand the lecture better when I give it next week.
Okay.
All right?
Yes.
Okay. So I'll see you guys again next week.
Okay,
And we're going to go through hypothesis testing. Be sure to be here to ask that question, and I'm going to go through that problem completely. All right?
Okay. Thank you.
Have a good night.
Good night.